Hello, I am Anshul Mittal, a research scholar at IIT Delhi, India, and today I'll describe to you a method that my collaborators and I have developed called ECLARE, which stands for Extreme Classification with Label Graph Correlations. Extreme classification is a new paradigm which has its application in ranking and recommendation tasks that pose specific technical challenges. Although the sets of labels is usually in the millions, any given data point is tagged with very few, say order log n labels. This makes it imperative for training and prediction to scale logarithmically with the number of labels to satisfy millisecond prediction and other latency requirements of real-time applications. Some examples for recommendation scenarios are Amazon related product recommendation or Wikipedia's related web page recommendations. Extreme classification deals with the scenario involving millions of labels. A peculiar characteristic of the scenario is the presence of head and tail labels. Most of the L labels turned out to be what we call tail labels, which comprises of 60 to 70% of the label space. These are very rare and very few training points, often less than 5, are tagged with such labels. Whereas some of the labels are popular head labels and have lots of training data. The challenge in extreme classification is always to predict the diverse and more descriptive tail labels. Before moving forward, let us fix our notations. There will be L labels in our universe and V tokens in our vocabulary. We will be given N training points, and for every training point we will be given two objects. First, we will be given the document text, for example the title of an Amazon product or Wikipedia web page. This will be given to us as a sparse bag of words vector xi that will tell us which words appear in the title of training point. Second, we will be given a label vector yi that is a vector of -1s and +1s telling us which labels are associated with the training point. ECLARE uses the label metadata in the form of textual descriptions associated with the labels. This is similarly presented as the bag of words vector zl for each label L. Learning model parameters using traditional machine learning approaches like one versus all is infeasible in extreme classification as the number of parameters scales linearly with the number of labels. So to address this and scale to millions of labels, most methods use deep XML framework. In the deep XML framework, extreme classification methods uses a shortlister S to first shortlist order log n labels and compute the relevance on only those shortlisted labels. Here, jointly learning a shortlister and L classifier is a challenging task. In literature, we have many scalable extreme classification methods. Unfortunately, most classifiers treated labels as just index. As a result, no one could explore label semantics with the document. To achieve this understanding, many types of label metadata such as label text was already available. DCAP shows that using label text to improve label semantics can significantly improve accuracy as well as scale to millions of labels. Now, DCAP could easily understand the label semantics. But is this enough? What about label peculiarities? In the given example, for a document, 85th Academy Awards, we have so many labels whose label texts are related to the document, but only selected few were relevant. Consider the case of Tony Awards. 67th Tony Awards and 80th Tony Awards have almost the same label text, but only 67th Tony Awards were relevant. This was not the case of missing labels. As it turned out, common denominator was these awards occurred in the same year. Can we map these peculiarities in extreme classification and improve our results? Here, challenge is to design a model which has this capacity to utilize such information and improve the accuracy while also considering XC requirements of order log L prediction time. ECLARE is the first extreme classification method to use label text along with label correlation graphs. ECLARE can infer label correlation from the ground truth itself, and ECLARE's two very powerful tools, which are label text-based representation and GCN-based label text augmentation, facilitates ECLARE to give accuracy 3% higher on precision 1 for publicly benchmarked datasets and up to 15% higher precision 1 for proprietary datasets of Bing. while offering predictions within milliseconds. This makes it suitable for real-world application. We will discuss each component in more details. Now let us go into further details for each component. ECLARE's lightweight and highly scalable embedding block maps bag-over document vector to dense low-dimensional representation using TF-IDF weighted sum of token embeddings, and learns a refinement vector using the frugal text embedding block E. All this can be easily done within 30 to 50 microseconds on a CPU. ECLARE uses shared token embeddings for both document as well as labels. This has two benefits. First, model size is reduced, and second, it allows tokens to learn from both document and label text. ECLARE computes long-distance label correlations to augment label text. Since ECLARE works in extreme multi-label settings, where issue of missing label is very prominent, particularly for tail labels, therefore using simple label co-occurrence leads to loss of many intuitive correlations. ECLARE solved this by using random walk with D-star. Here, Kangal dog was able to determine the correlated labels Bully Kutta and Tibetan Mastiff, which were earlier missing in the ground truth. After computing the label correlation graph, a careful normalization is very important, otherwise superhead labels will start dominating the graph. For the sake of brevity, we are omitting the details here, but we urge readers and listeners to refer to the main paper for more details. Traditional extreme classification method trains a randomly initialized one versus all classifier. However, tail labels do not have sufficient training data to learn those classifiers. ECLARE shows that using label text along with the proposed weighted label correlations can significantly improve the accuracy, particularly for tail labels. ECLARE's classifier has three components. First, label text classifier, which is based on TF-IDF weighted sum of label text. Second, graph augmented label text expansion, which we call this GALE, and a traditional stream classifier. These three components are combined using a shared attention block which computes label dependent weightage for each component to generate the final label classifier WL. Empirically, it was observed that for tail labels, graph components have more weightage than the traditional classifier, and vice versa for head labels. This showed that tail labels' paucity of training data can be ameliorated using ECLARE's collaborative learning-based classifier. Furthermore, at the time of prediction, we need to compute this attention weight only once, and therefore we can pre-compute them to reduce prediction complexity, which allowed it to scale to millions of labels at the time of prediction. As stated before, in extreme classification scenario, learning L one versus all classifiers is infeasible. ECLARE learns a shortlister to scale to millions of labels in three steps. First, L labels are clustered in K meta labels using label centroids. These centroids are generated using the incomplete ground truth. Therefore, clustering could be really inaccurate. ECLARE completes the ground truth by augmenting the label centroids using correlation graph matrix G. Clusters generated using these augmented centroids are superior and empirically leads to 40% improvement in loss of mutual information as compared to decaf, which uses the standard label centroids and the same fan out. Consider the given example. Decaf was clustering dog of Osu with Ferdinand 2 of argon, which is clearly a mistake. On the other hand, ECLARE was figured out this mistake and correctly clustered dog of Osu with Tibetan Spaniel and Tibetan Terrier. The label text features for these new meta labels is given by taking sum of label text bagovers of all the labels associated with that meta labels. Similarly, we compress the label correlation graph by summing the corresponding rows and columns. This is done just once during the training and can be efficiently computed in under 2 seconds even for millions of labels. Once we have reduced L labels to K labels and computed label text, ECLARE uses proposed one versus all classifiers to realize these K meta labels, which is done efficiently on a single GPU. The learned shortlister can now be used to sample order log L labels for final ranking. Now, we have seen all the components. Let us fit these components together to build the classifier. First, learn the encoder parameters using one versus all training on meta labels, which are far less than L. This would now work as a shortlister to give order log L labels which we would re-rank. Unfortunately, this style of shortlist is prone to error by not shortlisting co-occurring labels. To deal with this, ECLARE uses graph-assisted multi-label expansion or GAME, which boosts the score of correlated labels such that they are also ranked higher. This improves the shortlist recall by 5 to 6%. Using this improved shortlist of order logger labels, learn ECLARE style classifier by using the sparse gradients computed over the shortlisted label. This enabled ECLARE to scale to problems involving millions of labels as well as give state-of-the-art accuracy. Experiments were conducted on several public as well as proprietary datasets. Public datasets are available on Extreme Classification repository, while proprietary datasets were mined from the click logs of Bing. In particular, ECLARE could be 3% more accurate than DCAF, which also uses DeepXML framework but ignores label graph correlation. In product-to-product recommendation dataset from Bing, task is to recommend related products to the user based on the user interaction with the product. ECLARE could outperform every other method by the margin of 15% over all evaluation metrics. As well as ECLARE offered sub-millisecond prediction time. To understand the gains of ECLARE, here is a qualitative example from WikiC also. In this example, only ECLARE was able to determine which award ceremonies were held in the same year, whereas other methods were only able to predict award ceremonies that bear the token similarity to the queries. This can be attributed to the weighted correlation graphs. To sum up what we have learned so far, here are the takeaway points. ECLARE is state-of-the-art graph-based extreme classification method which uses label correlations into every learning process, which has been shown critical for the accuracy. ECLARE's proposed game step with the normalized graph can give lift to every extreme classifiers. However, ECLARE still remains state-of-the-art. Some of the future works for ECLARE includes learning document-document graphs to augment document embeddings and explore effective graph pruning for heavy tail datasets. Thank you.